Hey guys, welcome to part 6 of our online course. We will be covering foundations today, a brief introduction into the soil investigation, a site retention example, and also piling.
So one of the first things that needs to happen before we start the design of the foundations is a geotechnical survey. So there will be geotechnical engineers drilling a number of boreholes on site, the number depending on the variability of the soil. So this is required to provide advice on the soil conditions to help the design process. The type of information you'll get from the geotechnical survey is like the bearing capacity, which is the strength of the soil, which will determine the type of foundations, or the soil composition with properties such as the internal angle of friction and cohesion, and also understanding the settlement or displacement per unit of load taken from the load rundown. For different soil types, we're going to have different foundations required. So as the load gets higher and higher and there's more load to be transferred to the ground, the footing requirements will increase. So with greater loads and bad soil, we're going to have piled foundations. With rock, with high capacity, will be typically reinforced pad foundation. For gravel, which is non-cohesive and also high capacity, also pad. And same for sand. However, if it's loosely compacted, there will be risk of significant settlement. Clay, with load, it tends to consolidate. So it drains the water and then takes in water swelling as well. So the clay is cohesive with a low bearing capacity and is very compressive under load. So for clay, you'll have pad foundations to light loads or piling for the heavier loads. And when you've got bad soil with a high bearing capacity but not ideal, you'll need piled foundations. So the pile, you might need to take it down from the top layer of soil all the way down till you get a solid layer. And as we'll get into soon, the capacity of the pile is by the friction and the bearing capacity at the bottom. Here we have the different footing types. So first we have a mass concrete pad footing, which consists, as the name suggests, of a massive concrete and dug into the soil. And we have mass concrete strip footing, which is again just concrete with the soil over it. Here we got pile caps, so for greater loads, the load comes down here, and then you've got two piles on the edges, and a reinforced concrete strip footing. Also a raft slab, which might be used for the slab on ground alternative. So that's when we get the ground slab is being supported by directly by the soil below. Whenever we need to excavate soil, we need to have a system to hold the soil back. So on this side here, we clearly have excavated this soil, so we need something that is going to hold this back. So that's what a retention system is. What we're going to show today is a combination of soldier piles and shotcrete wall to hold a section of soil back. And in this case, we're going to have a vertical cantilever, but sometimes you might be able to use anchors, which will subsequently hold the soil back and act like pin supports. We will now go through some of the loading and setting up the problem to find out the maximum bending moments in order to design the piles. So here we have a retention system. First of all, we'll go through the load. So you're going to have a surcharge load, which will be governed by the traffic or the building adjacent. So this load will be rectangular, down like that. So this will be typically for, say, a busy road. It might be something like 24 kPa or 12 kPa for a not so busy road. Then also we're going to have the effect of the soil. So this will be, you'll get advice from the geotechnical report for this case, but for a cantilever situation, you're going to have a linear one, depending on the unit weight of the soil. So equals which might be about 17 kilonewton per meters cubed. So that'll be the live load, and that'll be dead load. If we use anchors in this situation, so if you have anchors coming through, this will actually be rectangular, but what we're showing here is the cantilever load case. And what we have supporting this load is the spring stiffness of the soil on this side. So the spring stiffness has springs on this side as the soil goes down. That counteract this. So depending on how good the soil is, you might require less socket length. So the first thing you need to do is find the socket length and find out how much the depth of this you need, and then also work out the bending moments based on this load. So the bending moment diagram is quite easy to figure out. You're going to have something like, for the cantilever section, you will have something like beginning like this, coming out like that, and then we're going to start getting the support from these springs. So M star, the maximum moment will be something like here, and that's what we need to design our piles for. In summary, what we have here is loading from the surrounding vehicles or buildings, such as the surcharge loader rectangular, plus the dead load, which is the unit weight of the soil. This is supported by the lateral spring stiffness, which is different for each type of soil, and also we have the socket length, which is a function of the cohesion and the friction angle of the soil. So in order to design this, the geotechnical investigation is required. Once we have designed the piles, we need to check the shotcrete walls. So the piles need to be designed for the bending moment and the deflection, like you would a normal column really, but for that bending moment and shear force. The shotcrete walls, however, span in between the piles for the same loading. So take a 1 meter load strip and then you can design it as like a 1 meter slab spanning between each pile and design this for shear. Once our loads start to get a bit higher, the piling requirements significantly increase. So the purpose of the piles is to transfer the loads from the weak soil layer to the solid soil layer. So there are two types of strength that the piles can get from the soil. And first of all, it can be friction from the soil, so the way the pile goes up against the friction, and also the end bearing. So if it's in a good soil layer, you might get some end bearing strength. So for some soils, you might get one or the other, but for the greater loads, you might need both. So basically, the bearing load or the bearing capacity plus the friction capacity must exceed the value from the load rundown, or in the case of lateral stability where you might have uplift, it must also be able to handle the tensile loads placed upon it. So there we go, guys, part 6 all done, our final part of the short course. So what we've covered is the soil or site investigation and the outcomes of it. Also a retention system, so we have an example of a shotcrete wall and pile combination that is cantilevering out of the soil, and the type of loads that are going on in this load case. Also, what we covered is piles and how piles derive their capacity and the different types of foundation solutions. There we go, guys, that's the end of the 6-part course. I hope you've enjoyed it, and more importantly, I hope you've learned something. So this is meant to be used as a starting point for all the design packages. There is obviously a lot more involved with everything, so ask smart questions to your senior engineers to get a better understanding. And for you guys, if you're wondering where I've been filming from, it's been Lombok, Indonesia, hence there's been cockatoos and roosters and motorbikes and a little bit of chaos. So thanks for sticking with me through all of that, and we'll stay in touch. If you can provide me any feedback, please send me an email, and that'll be much appreciated. So happy enjoying, and look forward to you guys having a very long and successful career.